All right, my friends, let's go ahead and take a look at the picture here. Let's see. So we've got, where do I want to draw this? How about over here? Okay. So we have a parabola opening downward. Vertex is at the point 3,9. All right, out 1, down 1, out 3, down 9, and then out 3, down 9. Okay, and y equals 0 is basically the x-axis. So here is our original bounded region, and it says we're going to revolve it about the y-axis. So let's draw that. Okay, and ladies and gentlemen, it's a bundt cake. There we go. There's a nice little picture of the 3D look. All right, there we go. So I've got the 3D look to it, and then I have kind of the typical washer cross-section type look that we'd normally give something like this, okay? Okay, so let's see. If we were going to use the washer method, then let's talk about how we would go about this problem. Okay, so for the washer method, we would need to be doing a dy integral, first of all. For us to be adding up washers, accumulating them, we would have to be scanning the y-axis. So we'd definitely be going for a dy integral. So we're looking for something like this. So volume is equal to pi times the integral. I can tell you the bounds would be from 0 to 9. We'd have to figure out what the outer radius is, and we have to figure out what the inner radius is, with respect to y, okay? Now, in order to figure out the inner and outer radii, we would need to solve for x, for the parabola there. So to do that, we'd take y equals the opposite of x minus 3 squared plus 9, and we'd start solving for x. So subtract 9, divide by -1, square root, don't forget plus or minus, add 3. And at this point, if you haven't started disliking this yet, you probably have started disliking this now. And so the point of this problem is that there's going to be more than one way to find volumes of revolution, because sometimes the washer method really kind of stinks. It's doable, but it's kind of a pain in the rear. So funny story, x equaling 3 plus square root 9 minus y is the right side of this parabola. Guess what x equals 3 minus the square root of 9 minus y? Guess what that is? Yeah, that's the left side of the parabola. Anyway, so, you could finish this out, but you'd have some work. And so I think I'm just going to say, and you'd have to keep going, and you may or may not like it. So you could put whatever, face you think, maybe you like it. Maybe you're like, yes, die hard, washer method forever. Anyway, maybe that's you. I don't know. Anyway, but however you're feeling about this, I personally would be left wishing there was a better way to go about it. And good news, there is. All right, my friends. So here you see a picture of the region that we're finding the volume of when it's revolved around the y-axis, and I'd like for you to consider for this problem maybe scrapping the washer method. And so notice that with the washer method, we ended up, in order to get those washers that we were used to getting, we had to do a dy integral. Well, what if we decide that we don't want to do a dy integral? We want to stick with a dx integral. Well, so if we did a dx integral, then we would partition the area with little segments that are perpendicular to the x-axis, like so. And then I'm going to show you what it would look like if we took these dx rectangles and rotated them around the y-axis. So maybe even do this for me. And this is a nice little visual aid that'll help you get unconfused later. If you will, take your index finger and stick it up, kind of like you're about to sing the This Little Light of Mine song. And basically take that and imagine that it's one of these rectangles that you see here. Okay, let's say it's this rectangle right there. And so take your index finger, and rotate it around the y-axis as if you're playing the role of this rectangle. And watch your finger, watch the path that your finger passes through. What shape are you drawing? So here's half of the shape that you would be drawing, and notice it's the back half of a cylindrical shell, and now here's the front half of a cylindrical shell. So in this little demonstration, the next thing that they'll show is what it would look like if you kind of had a finite number of dx rectangles and decided to rotate those around. It shows the back half first, and then it brings on the front half later, I think, just to kind of show you the full thing. So there's the back half, and now here's the front half. So that would be a good approximation of the volume that we're trying to find in example 1. So how could we get it to be more than approximation? How could we get it to be exact? That's right. We would need to be adding up infinitely many, infinitely thin cylindrical shells. So all we'll need to know is the formula for the lateral surface area of a cylindrical shell. And in the warm-up, we discovered that it's just 2 pi times the radius times the height.